Let's look at some examples, starting with one from a AP exam free response. Approximate the definite integral from 0 to 50 of v of t dt with a Riemann sum using the midpoints of 5 subintervals of equal length. Then, using correct units, explain the meaning of this integral. First of all, we see approximate. So we're not going to find an exact answer because we're using a Riemann sum. Remember, we see Riemann, we see R, we think rectangles. Now, approximate means we're not using an infinite amount of rectangles, so how many are they telling us to use? Using the midpoints of 5 subintervals. We're going to use 5 rectangles. They're all going to be of equal length. It's also telling us use midpoints, so not left endpoints, right endpoints, but midpoints. I have a table, so this could be helpful. A visual, a graph, will sometimes be even more helpful. So I'm just going to mark out, we're going up to 50 here. So how about 10, 20, 30, 40, and up to 50? And if we're using 5 subintervals of equal length, well, space that out already, but if we're going from 0 to 50, from 0 to 50, remember how we find those widths? B minus A divided by N, if they're equal width, 50 minus 0 divided by 5, they're all going to be 10 units long. So each of these 10 units wide. Each width is 10 units. And this time, instead of left endpoints or right endpoints like we practiced last time, it says use midpoints. So using the midpoints means between 0 and 10 exactly. So between 0 and 10, the first point is 5, and that's going to give us the function value. So remember that each area is the width times the height. Well, each width is 10, so 10 times a height, 10 times another height, 10 times another height, and so on and so forth. So remember, the fast way to do it is just factor out the 10 from each of the heights. So our first height we're going to find by getting the function value that corresponds with the first midpoint. So 5 will go up to the y value 12. So that's where our first rectangle is going to be, up there at 12 units high. So 12 is our first height. Plus, and looking at our second midpoint, 15 is between 10 and 20, and that y value is 30. So we are going a little bit higher for this one, up to 30. And that's our second height. Plus, and then we've got between 20 and 30 is 25. So 25 goes up to 70. It's a little bit higher. It's up there at 70. Here's our third rectangle, the height being 70. Next, 35. 35 is between those. That's at 81. So going up there to 81. 81, there's our height. So get a nice visual as we do this. And then finally, 45 is the last midpoint, going up there to 60. So just approximating, just to get a quick visual of what this looks like, and then computing it. So we've got all our heights times the factored out width, since all of them are of equal width, and we simplify it to 2,530. And what are the units for this? So we've approximated the Riemann sum. We show the work, very necessary for a free response. We've showed that work. We've showed a simplified answer, not necessary for a response. This is the part that's mostly looked for. Then explaining the meaning of this integral. So explaining the meaning of this integral using correct units. We should at least start by looking at the units. What are we multiplying together? Our x-axis right here, our x-axis is the time, and that's in seconds. So our change in x, the 10 represents seconds, and then the height is in feet per second. This is feet per second. So each of these y values that we're multiplying are feet per second. So let's take these units to the side here. Seconds times feet per second. What does that give you when you simplify that? That's right, just feet. So our answer is 2,530 feet if we're using units as well, which is always important in our free response questions. So using correct units, we've done that, the correct units explaining the meaning of this integral. We'll come back to this meaning. Let's take a look at another Riemann sum example. Looking at another Riemann sum example, again, from a free response. The rate of fuel consumption in gallons per minute recorded during a plane flight is given by this function that we're looking at in the graph and in the table. Approximate the value of this definite integral using a left Riemann sum. So again, we see Riemann sum, so we think using rectangles with 5 subintervals in the table above. So this time they didn't say of equal subintervals. Now they're telling us using that table above. So maybe they're of equal width, maybe not. Looking at the table, I see from 0 to 30, that's 30 units long. The next interval from 30 to 40 is 10 units long. So these are not equal width. So these are 5 subintervals used in the table. The left Riemann sum means that we're using left endpoints. So like how we went up from the midpoint, we're going on the left side this time. And the graph helps us here to see how wide actually the difference in the width. So our first subinterval from 0 to 30, right here we can see how that's 30 units wide. So our first width is 30. And the height of it, they said go up on the left side. So the left side is where 0 is. The left side is up here. Now don't count on the graph being accurate. Look at the table. So on the left side at 0, that's 20 units high. So 30 times 20 gives us our first rectangle's height. So that's that first one right there. Our second subinterval from 30 to 40, looking at the table, 30 to 40 right here, 30 to 40. Okay, like that, going up again on the left side. So again, I can't really tell accurately from the graph, so I'm going to go over here and look at the table. The left side is at 30 units high. So 10 units wide this time, from 30 to 40 is 10 units wide, 30 units high. So again, we're finding our areas by doing our width times our height. Okay, our next subinterval is 40 to 50. So 40 to 50, again, that's just 10 units wide, but now going up on the left side and over and down. So up on the left side gives us this high right here. The left side is at 40, and that's a height of 40. So our width is 10, while our height is 40. And then the next interval, subinterval from 50 to 70, so that's this subinterval right here, 50 to 70, that's 20 units wide this time, up on the left side, across and down. And at 50, that's a height of 55. Again, notice I'm looking from the table and not from the graph. The graph isn't very detailed enough to show me. So that width is 20 and the height being 55. And finally, the last subinterval, 70 to 90. 70 to 90, again, that's 20 units wide, going up on the left side, across and then down for our rectangle. And that height is 65, so 20 times 65. So we're going to add up all of those just to get a cleaner answer. 3,700, what will our units be? So what were our units for the time, the x-axis that we were multiplying? That says minutes. And gallons per minute on the y-axis, gallons per minute. So if we're multiplying the x-axis times the y-axis, the width times the height, we have minutes times gallons per minute. That gives us gallons. So 3,700 gallons is where we are for approximating that definite integral. Is this approximation less than the value of the definite integral? Well, remember the definite integral means that exact net area between the function and the x-axis. Well, look at this picture where we drew the left endpoints and the rectangles are all beneath the curve. So we're going to say that this is less, not because I see all the rectangles are under, but because what is the function doing? Why are all the rectangles under the curve? Because the function is increasing. So the left side will always be lower than the right side. So we will say less because we are using left endpoints and the function is increasing. So the left side will always be higher than the right side.